So today we're going to continue on chapter 3 on discussion of diode circuits. So we start with the general review of some diode circuit examples. I'm going to give you some direction as to what are the typical applications and as well as how do you analyze these type of diode circuits. And then we're just going to continue on discussion on the general operation of a diode and how do you conceptualize these based on our basic understanding or the simple model that we use, basically mostly constant voltage model, and use the model to generalize as to how does the circuit operate in a larger view. And the next thing we're going to talk about is one of the key important things. This is not necessarily only limited to diode circuits. We're going to apply this concept to different more complicated circuit with transistors. So we're going to start with the concept of what we call the large signal and small signal analysis. And there are key components you need to understand and as to follow up the analysis. So we're going to talk about something called the operating point. If you ever do simulation on SPICE, anytime you do a signal processing type of simulation, if you want to know when you apply especially AC signal analysis, you want to know where you stand, which is the operating point. So the option, I should say the command is point OP. I don't know if you know that because I used to use the very basic type of SPICE. So which is one of the one of the key concept or the key step before you do any operation analysis is something called defining the operating point. So it's called the point OP, if you remember that. But this is typically referred to as where you stand in the circuit. Or sometimes it's either referred to as the operating point or quiescent point. If the textbook uses quiescent point, typically the notation will be a Q, which means that when you're operating, the Q stands for you're standing at your quiescent point before the signal comes in. And then when you decide where this circuit stands, and then we're going to talk about when it twiggles a little bit, just a little move around this operating point. So when we do that type of analysis, we use something called small signal approximation. Remember, it's an approximation, so you stand for some tolerance in error. But this approximation will give us an intuitive sense as to how the circuit functions. And this would then, of course, generate something called the small signal model. We're going to talk about that. We're going to use that very, very often. So anytime you do analysis, you start with the circuit, find operating point, and then do a small signal equivalent model, and use that model for circuit analysis. So we get a sense as to when the signal comes in, how does the signal translate into throughout the circuit. And then the last, I think the main part or the core of this chapter, one of the key topic, I should say, is called the rectifying circuit. So we're going to spend a little time talking about what happened in your adapter. Everyone has a computer, and when your pad, you need to charge it up. You have an adapter. I didn't have an adapter, but you can see an adapter. So any of these adapters, what is actually inside the adapter? It comes from, what it basically does is that it takes in signals coming from the outlet, which is peak to peak, maybe 170 volt, AC signal 60 hertz. Everyone knows this is from the outlet, your power outlet. So you take the power from the power outlet and then transform into whatever you use to charge up the batteries, typically 3 volt, 12 volt, depending on your device. So then what is inside this adapter allowing this to happen, one of the key components is a diode circuit, which is the rectifying circuit. So that include these components. Basically, we're going to go through each steps and let you know how do you actually design this rectifying. If I give you a spec, meaning that I'm taking in what amount of current, there's a charging current. So there's spec on your adapters, which will allow you to transform into a certain level. You want to make sure that it transforms transform from AC to DC by rectifying, stabilizing. So the other thing is, how do you stabilize the supply even though you rectify it into only positive paths? We already talk about that a little bit, but how do you stabilize it and regulating the signal? So we're going to talk about each of the step that requires diode circuits to enable this function to be achieved. Okay? So just to sort of like a review, I'll give you a brief sense as to what typical diode circuit does. One of the example, if you remember, I'm not going to a very complicated structure. One of the example we use is something like this. Without the resistors, you basically have V1 and V2. In between this, if you're connecting in parallel, I should say in series, between these whatever you have as an input is typically a source. And then whatever at the output terminal where you want to deliver, we typically refer this to as a loading. So if you think about your system with a loading which you need to provide, and this is whatever source signal source is coming in. So in between input and output, I should say, let me use input and output. In between an input and output, okay? What is in between this if you're bridging this with a diode? So we have some example very similar. I'm just ignoring just skipping the resistors. So I might have circuit looking something like this with diode in both directions, in V1, V2, okay? If I'm using a constant voltage model, what this gives us is that I need to do two plots. Anytime you it's taking up too much space. So RL is referred to as the loading. It's loading whatever you need to provide. So then we need to plot two things. One is the transfer function. If you remember, if I'm using constant voltage model with VD on, whatever, I'm just giving a maybe 0.8 volt. Okay, so it will look something like this if you remember. This is a matrix, so this will be 0.8. This will be minus 0.8. And there will be a dead zone within where there's no signal passing, and it will follow afterwards. Something like this, okay? So basically what it looks like, this is the transfer function V in, V out. And if I'm plotting if I'm giving a sine V in as a sine wave, you should know how it turns out at the output terminal, the V out. You should be able to plot, let me get the color. Should be able to plot the same thing out on the same plot. So I'm plotting V out in response to the sine wave. Of course, I'm just giving arbitrary numbers. So let's say if this is 3 volt, peak level is 3 volt, minus 3. So you should be able to plot the response. Let's say if this is my boundary, which is 0.8 minus 0.8. So you basically there's a dead zone within. If you're let me try to plot it. So there are basically two zones. One is it follows input, and there's the dead zone. So you identify these are the dead zones. Within here, these are dead, meaning that it does not. It's within the dead zone. So it's flat at the output. So it does not follow within but when it passes, it will then offset by a 0.8. So it actually follows, but and only when it passes the dead zone. Okay, you should be able to plot. So the yellow will be your V out. So first, if you look at this plot, it basically just allow you to sense signal, which it's sort of like a filtering operation. It allows only signal that passing through the threshold. For example, in here, I'm setting my threshold to 0.8. It only allows signal when it passes 0.8. If my signal is very low, for example, if it's 0.5, you will see a flat line because it will lay within the dead zone for the whole period. So this is sort of like a detection circuit, allows it to exceed certain level. When it exceeds certain level, then the signal will pass. Okay, so the next type of circuit we already talked about is that you only have half of the circuit. So something like this. You're only limited in one direction. This is the rectifying circuit characteristic. So you should be able to plot the same thing. So it will look something like this, 0.8. And it will be dead. The dead zone will be extended because it will not allow the current to go in reverse direction, only allowing to go forward direction. And this will be 1. The slope will be 1. Okay? In rectifying circuit, they actually look identical to the output on the right. The only difference is, am I making it more complicated? I can actually draw it. No, then let me not do this. So your output response to the same input of 3 volts will look something like this. Only the positive half will pass and then remain dead and then positive half. So your dead zone will be any time. The dead zone will be when V in is smaller than 0.8. This will be a dead zone, right? So we'll be dead on the whole negative half cycle and also the limiting part on the because of the diode. So it will be less than 0.8, you remain dead, meaning that no signal passing, no current passing through this system. Okay? So these are when diodes are in series, it's bridging input and output. If you think about it, I can also place diode in parallel, which means that it will be in parallel to the load. So let's look at the third type of circuits. It's called a limiter. So the limiter circuit looks something like this. I also have my input here, my output with a load. So in between this, instead of having the diode bridging the two, I'm having the diode in parallel to our load. So it will be something like this. So if I try to make if I'm trying to make it more complicated, it could be something like this. V, B, am I, no. Just want to make sure my directions are right. Okay, so this will be VB1. This will be plus minus VB2. Okay? So this is when you place the diode in parallel instead of bridging the two. So this is called the bridging because it's bridging input and output. But I can actually place the diode underneath in parallel to our load, basically what I'm trying to say. So these type of circuit would then have an opposite response than this. It will look something more like, if I want to try to draw, you can actually do the exercise as we did before to find out the zones. But I want to just, following the concept, just to give you as to what is typical response of these type of circuit, it will look something like this. If you want to draw input, what it basically happens is that if I give you a very high positive voltage, it would then have all the current going through here if this turns on. So once it takes the current, what happens is that it will be clamping the voltage. We'll call it clamping of voltage, meaning that it would allow the voltage to be clamped at a particular level under here. This would then clamp your positive voltage. So if it's positive, let's say if V in is higher than VD on plus VB1, let's say. So then, let me do it slowly. So your D2 is on. We know that when it's positive, you don't actually see this. So if this is on, what happens is that this branch would then serve as a constant voltage source. So it will supply whatever it would allow. It would clamp this voltage like a voltage source. So what happens is that it will look something like this. When it passes, let's say, if this is VB2 plus VD on, what happens is that it would then remain at this particular, let me draw the circuit. So now we know that this one is off, D1 is off. So if I'm using my model, if I'm using the model, it will look something like this. Because that's off, you don't need to consider it. This will be a voltage source and another voltage source. V D on plus VB2. Load 0. Okay, if this is the case, what happened to your output, VL? Oh, I forgot to, I should have some, sorry. I should add a resistor to take on this bias. I missed that resistor. Okay, so this will be your V in. So if this is the case, what happened is that your voltage, if you look at the circuit, this will be clamped at a voltage of VD on plus VB2. Right? Because voltage source would then set this voltage to this level, so whatever voltage drop on here would then be sustained on this resistor. Okay? So this will then allow you to draw that it will be clamped. When it exceeds, what happens is that the diode will prevent any type of current which will sustain the voltage drop across here. And then this voltage will be clamped at a flat level because we have a voltage source. Remember, voltage source can take in any current to sustain the circuit to make this voltage stable. Your output will be stable if you're assuming that it's a voltage source. So this is when zone 1. If I'm in zone 1, if I'm less within this, when V in, it does not turn on branch 1. It does not turn on branch 2. Let me redraw this. So when it's smaller, if V in is smaller than the upper limit, higher than the lower limit. The lower limit to turn on is VB1 plus VD on in a negative sense. Okay? So if it's within our typical dead zone, in this case, if both branches doesn't turn on, your equivalent circuit, the equivalent circuit would then look something like this. right? If this is the case, then you follow a certain ratio, right? So this is that. So then you then have an R1 plus R2, R2. So you basically have a slope across this. Zone 2, it will be a flat line. And then finally, to the other end, the third end will be the same. Only one branch is on. So this will be when Vin is smaller than VB1 plus VD on. When it's less than this, what happens is that it will then turn on the negative branch. The reverse would happen, and then you would then flatten out. So your overall curve will look something like this. VB1 plus VD negative. Okay? So you will see that it's actually the inverse of the first circuit we refer to. So when in this circuit, you have the dead zone in the middle. When it passes the dead zone, then it follows. In this type of circuit, it's a limiter circuit. When it exceeds our limits, if I'm setting on these two boundaries, if it exceeds our boundary, it will then be clamped. It will be flattened out. So these are called the limiter circuits. So typically you will see, this is very, very common in integrated circuit. You have more like the protecting circuit is because when there's a large signal coming in, you want to make sure that it's limited within the region where it's safe to the circuit. So it's very, very commonly used in protecting circuits. For, I should say, protection circuits. So anytime you have input signal that exceed your boundaries, and I should say safety boundaries, if it exceeds your safety boundaries, then it will then be clamp, called a clamp. Your VL will be clamped at a particular level. It doesn't matter how VN increases, it will then flatten out. Okay? Is there a question? Okay? So I'm going through these examples just to give you a sense as to when you place your diode in various ways, how does it affect your output? So in this particular response, if you look at if I want to look at the time domain response, same as V in as a function of time, this is time. It would then look something like this. So if this is my V in, I'm not drawing in very well. Let's say if I'm setting my boundary with a simple circuit, let's say I'm just setting it with VD on. So then you will see that this is 3 volts minus 3. The white line is my V in as a function of time. So let's say if I'm setting my VB1 equals to VB2, and if it's symmetric, I'm setting it to 1 volt. So then my upper limit, upper bound will be 1.8, right? So I can draw a line. At 1.8 volt and minus 1.8 because I'm setting it the same. So then what is the corresponding output? It will look something like this. It will follow when it's within the dead zone, and when it hits, it will flatten, clamp, comes down, up, up. So it will be similar to this type of response. If there's attenuation, the slope will change. I'm just assuming that there's no attenuation. I'm setting up R2 to be much, much larger, then it would just follow. Oh, I know this should be all load. If you wanted to be following the response, you're assuming that R load approaching infinite, then it will just follow. If you're skipping R load, the effect of R load. But if there's an R load, then you'll see a slope. Okay? If I'm drawing this, I'm assuming that the gain is infinite. It's 1. If R load is in VL, so when R low is approaching infinite, or you're assuming open circuit, then this will be Vn. That is why I'm drawing it when it follows, meaning that when it's R low, it's infinite. So this is a special case when R low is infinite. Easier to draw. Okay? So just give you a sense as to what happened when you have diode, whether it's symmetrically placing the dead zone here when it's in bridging position. When you have only single end, you then have the rectifying characteristic. When you're having it connected in parallel to load, then it will then exhibit the characteristic of limiting signal. Limiting signal, if it exceeds a certain level, it would then clamping. So as I said, this is very, very, every time I see this output, it looks like something in a Korean drama. Do you know? They cut up the fruit, the head of the fruit. Okay, no one's watching Korean drama. Anyway, so they cut out the fruit, the top of the fruit, when it's very, very weird. So it looks like the head's being cut off, or the top is being cut off. Every time I see the clamping circuits. Okay, it's good? Any questions?都没有人看韩剧吗？没有共鸣啊。Okay. So just to give you a sense as how the diode circuits are being used. So the concept of having a diode circuit, one of the key characteristics, I want to emphasize once again, one of the key characteristics is that it has the on and off, it has two unique features. One is that, so if you look through these examples, you will see that a diode exhibits certain kind of feature which will be very suitable in delivering a certain type of function that we want. One is, of course, the next thing we're going to talk. One is that it would then provide a, we want to use rectifying characteristic. The rectifying characteristic meaning that it's come from the asymmetric feature of the diode. So if you actually draw, and the rectifying is coming from IV characteristic, if I'm plotting it this way, it looks something like this, right? So it only allowed current in one direction to pass. That's because it's a symmetric feature of the diode, IV characteristic, only allowing. So this is one of the features that is very desirable. And the other feature is actually this. As I said, so if it turns off, it blocks the signal. That's basically what it does in rectifying operation. The other is called regulating. We actually see that in our limiting circuit is that you actually want something that looks something like this. If I'm as I said, if I'm using a constant voltage model, it looks something like this. IV, constant voltage model. If I'm using constant voltage model, it will then give the model tells us that in this region, it looks something like this. It will be a VDON. This is also very desirable because it actually delivers something called a stabilized voltage. It means that it can provide any current, but deliver the same voltage. So whatever input I give or whatever current is flowing through the system, the voltage does not change, at least not a lot. So that's called a regulating factor. We're going to talk about these two types of circuit following today in the follow-up discussion. So these two features are very important in delivering the performance of the regulator circuits. As we said, it's very important in your adapter. You want it to be stabilized. Even though there's fluctuation, you want it to be regulated by this feature. And the other is, of course, rectifying, allowing only the positive cycle to pass for AC-DC transferring between AC and DC, power transfer between AC and DC. Okay? So before we actually dive into the particular two type of important application in circuits, other than these more general discussion, we're going to talk about the next topic today, which is the idea of having what we call the large signal and small signal analysis. So, what is we actually have already discussed something called the large signal. So whatever we did before, large signal analysis is basically this. Depending on your operating range, let's say from here to here, this is a large signal analysis. If I'm plotting that line, so this is V, as I said, from rail to rail, from all the from your boundary. So I have a negative supply voltage, I have a positive supply voltage. Let's say if I have a system, if I have a circuit or amplifier looks something like this, typically what we have is the most negative voltage is referred to as VSS VDD. So VSS will be the most negative voltage, and VDD will be the most positive voltage. Does anyone know why it's called SS or DD? If you're using bipolar circuit, it will look something called VEE or VCC. Yes, correct. This is actually the source of transistors. So when we come to MOSFET transistor, if you see SS and DD, you know that it's a MOSFET circuit because there's a source and drain. So we're going to talk about that later, but just to give you a sense as to typically what we first before we do analysis of the transfer function, you want to know the boundary of your circuit. So these are the supply will then give you the boundary of the circuit. So once you have the boundary of circuits, and we know that the input, so this will be my input, this will be my output. So I know, of course, the maximum voltage, positive voltage will be VDD, minus will be VS, because this is whatever being supplied to the circuit. So this will then set the range. And then we know the corresponding output. So if I'm drawing circuit, an amplifier circuit will look something very close to that. So that's called the large signal transfer function. You know at each point, so we know that V out as a function of V in from VSS to VDD. So you know the whole scope of how your circuit functions. You sweep the input and look at the corresponding output. So basically what we do is that you just connect this with a sweeping of input and then measure this with a voltmeter and looking at the output response as I sweep the input. So I should be able to get this once I have a device sweep from the most negative to the most positive. This is called the large signal analysis or your transfer function. Transfer function or transfer characteristic is typically how we analyze the large signal response of a circuit. So as you see, in most of these cases, you will see that it's typically operating in different ranges, and then it's typically nonlinear. Typically, it's a nonlinear response, meaning that it's typically cut into different regions, region 1, 2, 3, depending on where these devices are operating in which mode. So you get a nonlinear function. If you're having a linear function, it's very easy. You just get a gain. You have a voltage gain. But in this case, it would depend on where you're operating. The response, input and output response will be different. So what happened is that we then wanted to talk about what happened if my signal, I'm standing at a particular point, my signals are relatively limited to a typical type of range. So these type of transfer function, if you look at a inverter, I don't know if you take courses like logic circuits analysis, right? So you know that an inverter looks something like this. If this is input, this is output. So typically have an inverter 0 VDD. So for a CMOS inverter, the basic element in any of your computers, the inverter would then have a transfer function. What do you expect to look like? Does anyone know? This is a digital inverter, digital circuits. So let's say if this is 0 to VDD, VDD. So the range will be input. There's only positive range, so 0 to VDD. So this is Vin. I want to look at my VL. So what do you expect an inverter will look like? If you only know the logic state, when it's 0, it will be high or low. Excuse me. When it, let's look at it in a digital way. So, give me a good cup. So let's say if my input is logic 0, it will then give me what? Inverter. 1, correct. So it's logic 0, it will give me logic 1. If it's 1, it will then give me 0. So if I define my input 1, if I define 0 as correspond to 0 volt, 1 correspond to VDD. That's typically what is being defined. So I at least know 2 points in this plot. Where? When it's 0, it's supposed to be VDD. When it's VDD, the output should be 0. So these 2 points. But if I actually do the plot, it will be something close to this. So if you look at a good inverter, that will be your transfer function. This will be your VL as a function of Vin. Okay? So if you're dealing with digital circuit, what you're actually concerned is the end of your stage, meaning that if I have the whole stage of response, I'm only concerned it only stays at either here or here, at the boundary. It's jumping between the boundary. So if you're doing digital circuit analysis, typically a large signal analysis, because you're looking at the whole transfer function, and then we don't actually care about the middle too much, but you're basically looking at what happened at these two boundaries, because it's jumping between the boundary, jumping from 0 to 1, from here to here, here to here. It's jumping around. So it's a more large signal analysis. So anytime you look at digital circuits, it's typically a large signal analysis problem. So let's look at a different type of analysis, which is more the analog signal process. So the typical analog circuit process is, the analog example is on the left. This is an amplifier. So if this is an amplifier, so this is the analog part. So remember, anytime you talk about digital circuit, it would typically be a large signal because you're jumping from one end to the other. Okay. For analog circuit, what happened is that what typically being done, what typical operation of an amplifier is, let's think about what we actually want. So for an amplifier, this is my amplifier. So if this is my input, it's typically a very, very small signal. The signal is typically AC, because, for example, my voice changes with time. So if this is my signal, it's an AC signal is coming in. And then what I expect is that whatever being delivered at the output should be large enough. So what you expect is this is my input, and this is the output, for example. So what I expect is that if I'm having a small signal like this, maybe pick up by the microphone, which is, for example, 3 millivolt in amplitude. I wanted to make it loud enough for the speaker, to the audience to hear, so I'm amplifying my voice by this amplifier. So I'm expecting it to amplify it by maybe 50 times. So at least it will be somewhere in the range of, let's say 50 times, it will be 150. So I want it to be at least 150. So to provide a gain, a voltage gain will be somewhere around 50. So I want it to be amplified by this. So this will be my input. This is what we expect an amplifier would do. So this will be an output as a function of time. Just an illustration. Okay, so this is my input. So what we want an amplifier to deliver with a voltage gain. So this will provide a voltage gain, for example, for 50. So when I want to analyze this, if I'm looking back to my transfer function, what actually happened is that your input is at a very small range. For example, at the center, and it's only changing in a very small range. So if, let's say, if the slope is 50, I'm only concerned at this small, I should say, my concern is limited to this small region of interest. So this is the small region of interest which will provide my gain. So what it does is that then I don't actually need to look away from this particular point because my signals are very, very small. I'm only moving a little bit around this particular point. So then the point is that then I don't need to actually know what happened when it saturates because my signals are small. So I wanted to use something else to approximate what happened at this particular region. So to simplify the analysis, rather than going through the whole transfer function, I'm just looking at a particular point and how does it look. Okay? So if I'm already know that I'm standing in the middle, that's we typically refer to this particular, the center of the signal range where I'm biasing is called operating point. So for AC signal analysis, for analog signal, or I should say for AC signal, let me rephrase it. For small, we're going to talk about how small it will be, referred to as. For small signal analysis, especially typically referred to as AC signals. These small signals typically AC, it changes with time. We start with figuring out where the small signal is actually standing. So we set something, define something called the operating point. The operating point is, in practically, is being set by a DC biasing level. We're going to talk about that a little bit. And in practice, you set it to a particular point. I want to emphasize this again. This is a typical analogy I use in describing this, is that if I'm a singer on the stage, I want to know what happens across, if I'm using a large signal analysis, it's more like if I'm a dancer. I will dance from the stage, that end to that end, or I'm using up the whole stage, so I want to know what happened at a particular point, each point, what is the corresponding response the audience will receive, right? But for small signal analysis, it's more like a singer on a stage. When I want to sing, I want to find a spot where I'm standing, and probably not moving too much, a little bit, not too drastic. So it's small, if you think about it as a singer on a stage, what I actually want is to find a spot where it would give you the best acoustic response for the audience. So that's what the point of operating point. So typically what we want to do as a good designer, you're not only designing the stage is being set by the circuit. So once the circuit is being set, you have to determine where you want it to stand in order to give the best response, an acoustic response for the whole auditorium, or what you purposely, or you want to deliver to a particular judge, to the center of the stage. So it will depend on what's the purpose of your circuit, and then you set the operating point. So it's called a DC biasing level. You set it to stand at a particular point. And then we use, to analyze this, you do a small signal model for analysis of Vin output response in response to input. What does this mean is that once I decided, how do I decide where is my best point? Is that you want to look at this particular point. If I move a little bit to the left and a little bit to the right, what is the corresponding response? So I do some little tests to see what happened if I'm standing at a particular point, the output and input response. That will give me what we call the voltage gain, or referred to as the small signal gain. Because the slope is not the same. This is the same as when we talk about small signal capacitance, is that it corresponds to a small little difference. So your voltage, small signal voltage gain will be dV in versus dV out. So it would typically be the same as I'm going to define that a little bit. This will be determined as a small signal voltage gain. So it will be a small little difference when you're biasing at a particular standing point. And then that's called a small signal. You use a small signal model. So what basically being done in small signal model is to linearize it, because we typically have nonlinear response. You use a simple model to approximate it to make your assessment much more easier or more intuitive to the analysis of following up circuits. Okay? So let's take a break for 10, and then we'll come back and then give you some example as to how do you linearize, for example, this nonlinear equation. So I'm having a nonlinear equation. Remember, I as exponential VD, VT minus 1. How do you make it into a small signal model in corresponding as a function of where you stand? And yeah, in response to that. So this is the rectifying circuit that we just discussed. I don't know, clamping circuit, whatever. The clamping circuit is one side clamping. So this is the clamping or limiting circuit that we discussed. So what happened is that you start with a circuit, and because if my signal is not large, if not ranging from 0 to VT, it's only standing at a particular point and then change a little bit. So if I'm concerned, if my concern is this, I'm standing at something called a DC level, and then looking at a small signal level. So one of the convention, in order to, I know the textbook we used does not follow this convention, but I remember maybe Cedar Smith, they use this type of convention for notation. So I try to follow this notation in order for you to get a sense as to what is the DC biasing component and the AC signal. So the convention is, for small signal analysis, we then define V in, if I remember to use this. So I'm using V in both capital as the DC component, and then the small letters for all AC components. So this will be the DC, and this will be my AC signal. So this is the overall AC plus DC. So what does this imply? It implies that if I'm having a signal look something like this, if I'm drawing V in, the total signal, that's the combination signal. Both the DC and AC, it will consist of a certain level of DC level. So for example, this is 2 volt, and then plus a 2 millivolt sine omega t. So your signal, your overall signal, this will be my DC. So this will be V in at 2 volt. So the small signal will then fluctuate from, so it will look something like this. This will be my total signal. Add this 2 volt and then fluctuate with a signal level of 2 millivolt. Amplitude is 2 millivolt. Okay, so this would reflect the amplitude of your AC component. So I will try to follow this convention so that you know that which is the DC part, which is the AC part. So correspond to the circuit, it will be a DC bias plus a small signal input. So this will be a small signal input that changes, and it has to be small. I'm going to use that word a lot. So when you use the small signal, it only changes a little bit. So you start with what? You start with the circuit architecture. And then what we typically do is that once I have the circuit, I typically, in between, you could do large signal analysis. So once I have my circuit, for example, this circuit, I can draw the large signal plot. It will look something like this. Remember, if you remember, it will look something like this. Right? It would then this is my large signal response, input and output. So then I would like to decide where I will stand, depending on what the circuit is. If this is a regulator circuit, maybe I'm standing right here. So if this is my V in, so this is 2 volt. I'm actually exceeding my boundary. For example, this is 0.8. So I want to look at what happens if I change a little bit. What do I mean by changing this? So this is my change. Amplitude, this is the 2 millivolt change. So if I'm changing here, I want to see what is the output response. So this is what we're trying to do. So you do the analysis, and then you decide where you're standing. For example, I'm designing a regulator circuit. I wanted to stand. Of course, I wanted to exceed 0.8 volt because I want it to be flat. Therefore, I will determine where I want it to stand. So we do something called a biasing design. What is a biasing design? Is to set. The purpose of a biasing design is to set V in at this 2 volt. So I want to make sure that I'm actually at this point. The way to think about this, I also use the stage analogy, is that if you're Mayday? Yes, whatever. So if you're a singer, you want to be placed, if you're doing a concert, for example, you want to make sure that you're actually at this particular light spot. For example, if you're singing, you have the stage would set up the light spot, right? So you're actually standing at this particular point. So, but you need something to place you at this particular light spot. Okay, so this is called the biasing design. You have all this equipment and all these frames allow this singer to come from the sky, for example, and land it at this particular light spot. It's the desirable point that you want to be placed in. That's called the biasing design. I'm going to talk about biasing circuit a lot because that's not trivial, because you want to make sure that you're landing at this particular point, your desirable operating point. Okay, so you pick your operating point and you set up this stage so that you will be landing at this particular point. So this is called the biasing design. And then once you have this biasing design set, you then know your operating point. So then you land at this, the biasing design to set. So now we know that once it's being set, it's at 2 volt. So this is the process of setting. This is when it's at this point. So when it's at this point, what we do is that we then go to the next steps called small signal. Let me write it clear. Model. You created, we actually already have small signal model through this. So we're going to establish each of the nonlinear element you will then seek its small signal model. So I have a diode. I will then create something called a small signal model. And through this small signal model, and once I know where I stand, I could use this small signal model to extract what we call the small signal parameters. And then we could generate a small signal equivalent. Once again, we use this a lot, equivalent circuit. So you generate an equivalent circuit. So starting from this, if I'm only looking at the small little change, I could redraw the circuit. It's like if you're using a constant voltage model, you could assume that when it turns on, it would then use a simplified model. So I would then generate something called a small signal equivalent circuit based on this. Don't want to break it. But then this would then look something like this. For this particular circuit, it will look. We're going to talk about how you arrive to that. But this is the equivalent circuit that we're going to arrive at. Even though you don't know how we get to that, but then it will be simplify as this if you're only interested in small signal. If you're only interested in what happened if you're standing at this operating point, only doing little changes, little movement, very small movement, then I can tell you the response, the relationship between input and output through this small signal model. And here, this is the small signal parameters you extract. So I'm just laying out the works we're going to follow when we do examples analysis. So basically what we actually, once again, I want to emphasize this again. You start with a circuit. So this is the circuit architecture we're going to use. And then depending on where you want to set, you set it to a particular point, determine as operating point where you want to stand. And then this is your best operating point you want the circuit to be at. And then once it's being set, you then twiddle a little bit, move a little bit, and look at what happened if I move a little bit, what is the corresponding output. And you're only interested in that because you're the singer, you're not moving too much. So I can use this approximation only looking at if I'm staying, for example, staying within the spotlight. If I'm only staying within the spotlight, this response will be legit. If I'm moving out of the spotlight, it will be in other region, then that's no longer valid. So you want to make sure that your signal is small and it's within the operating region. Okay? So let's go through an example so you get a sense as to how does this process go, how does one go through this process. So before we do that, we actually only still have something lagging, is that how do you determine a small signal model? Because we have a nonlinear element in the system. In this case, what is the nonlinear component? The only nonlinear IV characteristic, this is a linear component. These are just signals. So the only nonlinear component is this. As I said, you have something like this. IV, it looks something like this. So based on this exponential model, you want to create a small signal model for the device. And here is a diode. Here we use the diode. So we only have one device, one nonlinear device so far. So we want to establish a small signal model. We're going to do this for all the devices we introduce in this class. So we're going to have the small signal model for diode. We're going to for transistors, both transistors. So we're going to establish that when we enter the discussion of having transistors. But now we only have diodes, so we're going to establish a nonlinear response. So the small signal, how do you generate a small signal model? How do you describe? Basically, how do you describe a diode's current voltage relationship when it does not move too much? So small signal model for a diode. So anytime you start with this, we start with a ID. So basically what you want to generate is that you want to generate a relationship between diode current and diode voltage. But instead of having it's like small signal, it's like where you stand and then you move a little bit. So let me try to draw this. So if I have an exponential, I already know that ID, the DC characteristic ID versus VD, based on our exponential model that's more precise, it will look something like this, right? So this is ID as a function of VD. Based on exponential model, which I as exponential V D VT minus 1 square. Okay? So that's the basic equation we start with. So think about what we're trying to solve. We're trying to see the problem. The setting now is something like this. So if I want to generate a diode circuit, diode small signal model, I actually want to know what is the current bias relationship when I'm not moving too far from a particular point. So it will look something more like this. So the issue is that you start with a quiescent point. So let's say if I'm standing at this particular point, I'm defining as VDQ. This is my operating point or quiescent point. I'm using Q because it's less confusing than O. Operating point. So let's say this is my operating point. I'm starting with this operating point. What I want to see is that if I'm from this particular operating point, if I'm moving a little bit, if I'm moving away from the center by a little, so let's say this is VD, a little small little signal changes, variation at this particular point. This is the magnitude of my fluctuation. And so what I want to look at is what is the corresponding change. Okay? So let me try to emphasize again. Once you stand at this particular DC level, the corresponding level at current, this is typically referred to as IDQ. So you stand at VDQ, you look at IDQ. And then when you change this from the center, when you move a little bit away from the center, what is corresponding response? Is a corresponding changes in your output. So this is corresponding changes in current. Correspond to the signal change. So there is a small signal change and then corresponding diode current change. Right? So if you look at this circuit, it will look something like this. How do I actually test it? Is that I have a diode. Remember, if I'm doing DC analysis, simply apply a fixed level. So if I'm applying a VDQ, if I'm doing small signal analysis, so I'm going to superimpose a small signal. So then the corresponding current, the total current, remember our convention, so there will be a current. The current will then consist of two parts. There is the DC component and the AC component. So we know that at this VDQ, there will be a DC component, DC current level, plus a small signal component. Okay? So this will correspond to this. Your VD, your changes in voltage will correspond to the changes in your current, AC current. Okay? So we wanted to create this. You can basically actually do this exercise without creating a small signal model. You just do the exponential model. You can get the current and then subtract it and get the current at this particular bias point. So you can actually just simply use the exponential model. But if you're using exponential model, it will actually make the equation very complicated and lack intuitive sense. So what we basically wanted to do is to create something called small signal model.